Hey guys, this is very strange, but I'm actually in my basement recording this for you because the first 10 minutes of lecture weren't on the original video. I stayed after school today to record them all, and when I got home to post the video for you guys, it deleted everything. So here I am, pretty late at night, trying to get this video done for you in my basement. So you can see behind me some of our basement stuff. Pool table, and we're actually recording on the poker table right now. So I'm going to try to get through this super fast, and there was more, but I'm going to go quickly. So you do have your slides where you can read sort of what someone would need to teach this, and so that's on the right-hand side of your notes, so just read through that. All right, so here we are about kinetics, and so essentially what kinetics are is just telling you how fast a reaction occurs. And it's telling you that there's 3 different ways that we can examine the rates of reactions. So we can have the rate of disappearance, the rate of appearance, and then the last one, the rate at which the overall reaction proceeds. So if something disappears, we can say, oh, it went away that fast. And if something appears, we can say it went, it came about that fast. So we can examine by looking at final and initial spots to see what the concentration is. So here's just showing you that the rate of disappearance is going to have a negative sign because when we do change in concentration over change in time, when something is disappearing, your final minus your initial will always be a negative number. So say your initial was 10 concentration, 10 molar, and then it goes down to 5 because it's disappearing. Well, then 5 minus 10 will give you a negative 5, so you're always going to have a negative number. But our rate numbers can't be negative, so we have to put the negative sign in front of it if it's a disappearance. If it's an appearance, then we're fine. We don't need to put a negative number in front of it. And so always the way you find rate is change in concentration over change in time, which means that our units will be molarity over time. I'm going to pause 1 minute. Okay, continuing. All right, so the next slide is just showing you how they're all related. And so it's saying that the disappearance would be the 2 negatives, and then we can relate them by looking at the appearance of the 2 products. This slide is sort of silly. All right, the next slide is talking about how we can examine the rate of a reaction by looking at the slope of a line tangent. The AP exam never asks you to actually calculate the slope of a line tangent, but they do want to know that you're able to say the way to do this is by looking at the line tangent. So for example here, we have the reactants are in a 2 to 2 to 1 ratio, and then we're increasing, our product is starting at 0, so concentration is 0, and then it's increasing over some time. And then we get to the flat part, which should be equilibrium. So you guys know that when the concentration doesn't change anymore, then we're at equilibrium. But if we want to find what the rate is at any point in this graph, so obviously this is really steep, so products are being produced quickly, but then we start to level off, and then when we get to equilibrium, the rate of that production is no more. So if we take any point on the graph and we draw a straight line to it, it's called a line tangent to the curve. So if we draw our tangent line and we take the slope of that tangent line, then we can find the rate at that specific moment. You can do that at any point on the graph. So one of the AP free response questions that I gave you in the packet is going to ask you that, and you'll just say that you'll find the slope of the tangent line. Oops. All right, so then this graph is really useful because if I don't give you all these labels on here, can you predict what each of those lines mean? So basically we're starting at 0 and ending up somewhere, 0 and ending up somewhere. So those clearly have to be products. We're starting at a reactant, high concentration here, decreasing down. You can tell that these are in the same ratio to each other because they have the same disappearance and appearance rate. And then you can tell that this one is half the appearance of this red line. So this must be a 2 to 1 ratio. Same thing with this, it's just showing you that this is our starting point. Time is equal to 0, time is equal to 60 seconds. We start at 15 molar concentration, 0 and 0 for our products. And then we decrease, so pay attention here, we decrease by a factor of twice as much as we increase. So this went from a 15 to a 5, which means that we lost 10, but then at the same time, over 60 seconds, we went from a 0 to a 5. So this is decreasing by a factor of 2, and this is increasing only by a factor of 1, hence our coefficients are only 1s there. So this is showing how we can actually calculate the rate of this specific reaction. So we take our T final, 5 minus 15, over time, 60 seconds, and then we can find the rate, and we can also do that for our products. So 5 minus the 15 over the 60 gives us our rate, and then the same thing here is showing us the rate of the appearance for our products. Or what you could have done is just taken the rate of your reactant and halved it, because if you look back here, we recognize that the coefficients were a 1, And so if we took half of that rate, then we would get the same answer as doing the rate of appearance. All right, so when you write a rate law on the AP exam, they're actually asking you to literally write the words rate equals K. You will always write that for a rate law. But then what's inside the brackets will change, and then those M and N superscripts are going to change also depending on the order of the reaction. So here your K value, rate is always going to be in molarity over time. Your K value is a constant that is specific to the reaction and at a specific temperature. So we will eventually calculate this value here. And then your M and your N are referring to the order of the reaction, and they will be numbers that we're going to plug in. Those M and N values never correspond to the coefficients. So I know when we did equilibrium, we would do products over reactants, and we would raise them to a power that was related to the coefficient that they came with. But in this case, we ignore any coefficients. They do not become the superscripts. All right, so we're going to have 3 different order reactions. You can actually have more, but they really just focus on the first, second, 0 first and second, but you can definitely have more orders. And again, you can't predict them from the balanced equation. So for a 0 order reaction, we're looking at essentially what happens to the concentration and then what happens to the rate. So I'm going to write down a little chart for you, and then we're going to examine what happens. So when you double the concentration, so envision that you're the chemist, you're in the lab, and you take one of your reactants and you double the concentration of that reactant, and then you examine the rate. If the rate does something, like say it doubles, then it's going to be a certain order. Say it quadruples, then it's a certain order. Say it does nothing, then it's a certain order. So for this specific one, let's see if we can see this. If it's 0 order, and then we double the concentration, so as a chemist we go ahead and we double the concentration of one of the reactants, and we see no change in rate. If we see no change in the rate when we double the concentration, then it will be a zero order. And that's what this slide is saying here. So we don't see any change. So what you'll have to do on the exam and on multiple choice questions is recognize that your rate will just be equal to the K value for a 0 order reaction. So just anything raised to the 0 power cancels that out, and it just gives us the K value. So even if we double A, which is the concentration of A, double one of your reactants, then it's 0 order if the rate doesn't change. If we get a graph that is concentration versus time and it is a straight line, then that means it's a 0 order reaction. So we're going to focus later on, I think in lecture 3, about graphs. And you're going to see different axes for your graphs, and if they are straight lines, it tells you if it's a first order or second order reaction. But that's not till lecture 3. So for lecture 1, when you look at this graph of concentration versus time, you have to remember that this means it's a 0 order reaction. What it means by being a straight line is that if this were the same graph, and instead of it being like this, we saw something like this, that is not a straight line. So we would say that this is not a 0 order reaction. It has to be a straight line to give you a 0 order reaction. All right, so then the next one is the first order reaction. So if it's going to be first order, and we double the concentration, and we see that the rate doubles, then it's a first order reaction. So rate doubles. So this is what you're going to sort of memorize, right? So far, if we double the concentration and no change occurs in the rate, then it's 0 order. If we double the concentration and the rate doubles, then it's going to be first order. If you evaluate, again, this, and I take my rate equals K, I know it's really hard to see, but you have the slides, rate equals K, and then 2 times X. X is your concentration of A. So if I double the concentration, which is our X value, and I see that the rate will double because it's raised to the first power. So that's a first order reaction. So the rate will double. That's what this final 2 means, that it's going to double. The last one is if it's a second order. So if we double the concentration and the rate quadruples, then it's second order. So again, if this X value is just concentration and I double 2 times the concentration for a second order, so its power is 2, would be 2 squared. So that would be a 4. So it would be quadrupled. So for a second order reaction, the rate quadruples. So you need to kind of write this down and make sure that you memorize that. So you're going to eventually evaluate data, and the data will be given so that you evaluate rates, and you'll see if it has no change, double change, or quadruple change. So there you have that. So what if I told you that this was a rate law, and I'm asking you what will happen to the rate if I double the concentration and the order of the reaction is 3? So go ahead and take a minute to think about that. So take this same slide, do rate equals K, in parentheses is 2x, but now your superscript is a 3 because that would be a third order reaction. So if we did 2 times 2 times 2, we get 8. So our rate would increase by a factor of 8. I don't know what the correct word would be because double, quadruple, 8. That's what it would be. If it was a fourth order reaction, consider what that would be. So really just use this equation, if I give you a multiple choice question to evaluate what the rate would increase by a factor of a certain amount. All right, so this is how we're going to express our rate law, and the M and the N will be predicted by looking at data that you're going to see in just a little bit. But if I ask you for the overall order of the reaction, literally all you do is add up your superscripts. Very, very simple. So say you didn't know the order of a reaction and you couldn't figure it out from, this kind of information, then certainly make up an answer, write the rate law, and again, remember a rate law always literally says the word rate equals K, and then you have the concentration of the substance and then these powers you're going to calculate. But if you didn't know them, just make something up and then add them up so that you get the next question right. What's the overall order? Literally just add them. All right, so this is the last slide that's super important for you, and this is really why I wanted to make sure I lectured. You have to not calculate, but determine what the units are for the K. And so you could simply memorize this slide, but it's kind of ridiculous to do that. So let's just figure out what the units of K are based on what we know rate has to be equal to. So rate's units are always molarity over time. So really, it's going to look like this. So rate's units are always molarity over time, but really, I'm backwards here. We always want to see M over S, molarity over seconds. And so if we're calculating for a rate law that is zero order, then it's just going to be rate equals K, right? That's our rate law for zero order because we know that if something's raised to the 0 power, it cancels that out. So then if my units for rate, it has to be M over S, then my K value for a zero order reaction has to be M over S. So M over S is equal to K, therefore K has to be equal to M over S. Follow that? Now our first order reactions are rate equals K, and then you can see here, times the concentration of A. All right, so again, if rate has to be equal to M over S, I'm going to write that, and I'm going to say my K value is what I'm solving for, and I know that concentration units mean molarity. So now my K value has to be equal to 1 over S in order for me to get M over S. So the units for K in this case are 1 over S. Okay? All right, the next one that we'll try is the units for, we got some scribble here from the kids. All right, so we're going to look at our units for second order reactions. So if the order is second order, we know that my rate law is going to be equal to K times the concentration of something, so we'll put molarity, raised to the second power, right? Because the power has to be a 2 for a second order reaction. Well, I put a capital M in there because the units are molarity. And again, my rate units have to be M over S is equal to K M squared. So at this point, I need to get my K to look like M over S. And so my K value at this point has to be equal to a 1 over M times S. So K has to be equal to 1 over m times s, which then would give me my square and this to cancel. So I'll just have m over s, which is what I'm looking for. All right, so just pause the video at this point and you guys try the rate law, the order of the reaction for a third order reaction. Go ahead and try. So for a third order reaction, we're going to have rate equals km cubed. Therefore, k has to be equal to 1 over m squared times s. And then that will make sure that we get the m over s value that we're looking for. So when you look at your slides and you see everything raised to a negative power, anytime that you raise something to a negative power, it just means put it in the denominator. Okay, so here's your example, and now you get to move on. Have a great day. Okay, so let's get started solving for rate laws. So today the data will be given to you with experiments, and I am going to show you one AP question where you end up with 3 reactants, and that usually is a little bit challenging. So remember, you can only have one variable at a time. You can't change concentration of 2 different reactants at the same time and measure what happens to the rate of something. That doesn't work, right? Like, you have to only examine one variable at a time to determine what happened to the rate. So the one question that I will show you is that the concentrations for the third one are not possible to do that for, and you'll end up plugging it in. So that's why I'm showing you. You can do this definitely in your head, but I'm going to show you mathematically how to set it up so that if you do get a scenario where you have to solve for the exponent to figure out the order, you can do it. So for this problem, we're going to solve for the rate law for this, then the rate constant, and then the order of the overall reaction. So the first thing that you do is you're going to look at, like we discussed already, your experiments for NO where H2 stays the same. So that's experiment 1 and 2, and then I showed you that you want your larger number to be in the numerator and the denominator. So I'm just going to rewrite this for you. So it's rate, we're going to do experiment 1 over experiment 2. These are the experiments that we're choosing. And we're going to put 0.0900 over 0.0225. And then that's equal to K and K. And then we're going to do our concentration of NO. So NO is in experiment 1, 0.20, times the concentration of H2, which is 0.30. Experiment 2, it's 0.10. And experiment 3, it's 0.30. All right, then I'm going to put these little M's and N's here. What are my M's and N's? They're the superscripts basically to tell us what? The order of the reaction. So this is why we just cancel it out so that it's not part of it so we can solve for it. So if you take your calculators out, you now can solve for the exponent, which is really what you're doing when you look at that chart that we made. You're looking to see if it's doubled and it quadruples or doubles, stays the same, whatever it might be. But you could actually just calculate it without memorizing that chart. So you get 0.09 divided by 0.0225, which should give you that 4, right? And then you take your 0.2 divided by your 0.9. So then our k's, we're just going to cancel them out. Our 0.2 divided by 0.1 is obviously 2 raised to the mth power. So you can see that if you double the concentration, it quadrupled your rate here, right? But what would be the power of m? 2, right? Like m is a squared. So if it's squared, then that would give me the rate of 4. So then that must mean that the rate for the order equals 2 with respect to NO. That's usually what they say. With respect to NO, the order is 2. So realize it's the same thing as memorizing this. In a second order reaction, when you double the concentration, you quadruple the rate. So we could have just looked at this and said, all right, this is times 2, this is times 4, therefore this must be second order. That's really the simplest way to do it, but I just keep reminding you that they're going to give you harder problems, and then this would be the approach so that you could just calculate it rather than trying to just mentally quickly do it. So if they give you a third one, and you know the order because you've solved for it, you would just put the third one in here and calculate. You would just eventually solve. All right, so now we have to find the order with respect to H2. So now you're going to look for NO where it stays the same. So NO stays the same between experiments 2 and 3. And it went up from 0.2 to 0.3 and 0.015 to 0.0225. So you guys try to solve this piece right now. So you can do it in your head. You can use your calculator for sure, or you can actually solve. So I'm going to show the work again for solving for it. So experiment 3 and 2. So I'm going to put 2 over 3. So that's, the rate is 0.0225 over 0.0150. And that's equal to k over k. And now it's 0.10. And we already know that order is 2, right? But that's going to cancel out anyway. And we're solving now for the nth power there. So you, again, don't need to calculate it, but you could. So 1.5 is equal to 1.5 to the nth, so what is n? 1. So again, if we double the concentration and it doubles the rate, then it's the first order. This isn't double though. So do you get though that it doesn't have to be double? It's just like if the same thing, if you do the same, then the same thing happens, then it's 1. That's why memorizing this is good, just to kind of pay attention to it if it's like quick data that you can see, but you could just calculate it too, okay? So then the next part says find the rate constant at this temperature. So now we're solving. Let's first, though, I'm sorry, letter A says write the rate law. So the rate law, remember, is no numbers except for your superscripts. And when you write the rate law, you literally write the word rate and K, right? K is going to be some constant for this specific experiment times the concentration of NO. And what order was NO? Second order with respect to NO, and with respect to H2, it was first order, so we just leave it like that. Simple, right? So I'm telling you, this test, you guys, some of you, your grades I just looked at from first marking period, second, and then third, consistently across the board, most of you are low right now compared to what your first and second marking period grades were. So I do realize that acids and bases was hard, but this, I mean, get 100 on this test, or really close to it. It's definitely achievable. It's short, and it's simple stuff like this, right? All right, so the rate constant now. So we're here. I just showed you that the rate order for NO and H2. Okay, and now we're going to find the rate constant. So you're literally going to solve for K. So what you're going to do is you're going to rewrite your equation. See how it says K equals now. So you're just rearranging the algebra there. And you can pick any one of your experiments to solve. So you could pick experiment 1, 2, or 3, and you should get the same K value for all of them because it's consistent. So you're going to pick an experiment and you're going to plug it in. So all of you pick one. I'm not going to show you which one is picked here because I want you all to be able to realize that it doesn't matter which one it is. You can pick any. And then plug in your own data for that specific experiment. The answer up for you, so you guys all could have chose any experiment. Did you get this? Yes. All right, did you get the units?
Yes.
So realize that the questions always say, when they ask you to solve for K, which is the rate constant, they will specifically say, solve for the rate constant with units. Well, that's what they're looking for. Do you see, Argo, why I don't want you to memorize? Yeah, it's just too much information to have to keep memorizing. Okay. So the overall reaction is third order because you add up your superscripts, so 2 plus 1. I mean, these are, honestly, I love getting kinetics questions on an AP exam. When I see that you guys get them, it's kind of like free points because this is one of them usually. What's the overall order? So even if you were wrong in your A and B, do you see why I say look for points? What if you had no time at all? Just write an answer in A, what it is, whatever you think it is, and then just add them up and you get a point because it's going to be consistent with parts A and B. They have to make it consistent. All right, this is what I was saying I should have gone through with you, but I forgot that that question was on there for your homework last night. So just recall that when we do Beer's law and spectroscopy, that it's all about light shining through the sample. However much light is there would absorb that light. The substance, the concentration of the substance is there, would absorb the light, and then transmittance is going through. Absorbance is how much is being absorbed. So you do that little math problem to relate transmittance and absorbance, and they usually will give you absorbance there. So I think you all kind of remember that from the beginning of the year. What you do need to recall is Beer's law for this. So A is absorbance, little a is molar absorptivity. Now this one is a constant for that sample. So you can look this up, or you'll calculate it. So it's going to be either given or you solve. I have seen before a few questions, not that many, where they do give you absorbance data for a kinetics problem. It's not my favorite, but they might give it to you. So then B would be the path length of the sample, which means like how big is your cuvette. So the cuvette size. So it's usually like a 1 centimeter or whatever they might give you. And then the concentration would be what you're really solving for is C, right? So they'll give you some absorbance data. These are not that frequent, but I'm going to show you how to do them. So here's the data that they present. See why I don't really like it? It's a lot of stuff. Yep. So this is what the lab is based on, and that's why these are here. So if they gave you a lab-related question, you would understand how it works. It says 3 experiments were conducted at 25 degrees C for the following reaction, which occurred in a 1 centimeter cuvette. So you mix these 2 substances together, and the solution looks green. Then, as the reaction proceeds, it goes completely clear, right? So you're measuring, you literally take your cuvette, and over time, every 60 seconds, they're putting their cuvette in the spectrophotometer, and they're measuring the absorbance of that sample. So you can see that it was green going to clear, green going to clear, green going to clear. Essentially, that's what they're showing you. And you have these 3 different experiments. So what are they doing in each of the experiments? Changing the amounts of what? Your reactants, right? Your concentration of your reactants specifically. And you'll notice that they keep them constant in 1 and 2 here, and then here it's constant in 1 and 3 for C. So again, you're only changing 1 variable at a time. So it says find the rate law and the rate constant at this temperature, the same thing as before. So really what we need to do is determine what you have, like from that last slide, what did you need to figure out the rate law? You need to know your concentrations and your what? And your rates to see what happened. So if this is the data that you're given, you know your concentrations, but you don't know your rates, do you? What is rate? Not just final minus initial what? Concentration, change in concentration over time. So you could essentially calculate change in concentration over time from this data, even though it says absorbance, because then you can do what? Beer's law, A equals B, A, B, C, which is why I hate this problem. It's just so long. So essentially what you're going to do today is you're going to make your own data tables from this lab. This is essentially the lab that I gave a really long time ago, but we only have 1 spectrophotometer, right? So for every single one of you to have to run to the spectrophotometer every 60 seconds to put it in, you're not going to get the time that you need to do it, and then our data is all going to be off, and you're going to be frustrated when you're trying to make your own graphs. But this is essentially what it is, right? So try to follow along here. So we're going to use A equals ABC, and then we'll come up with our concentrations at these points. We'll do change in concentration over time, and then we'll come up with a rate for each of these experiments, and then we'll make our own data table. It's just awful. Okay, so first step, find A for the colored reactant. What is A? Molar absorptivity. They didn't give it to us, so we have to somehow calculate it. So if you go back to this data, you have A equals ABC. Do we have enough information to come up with little a? A equals ABC. So how are you going to find that? Yeah.
graph, that's your big A, big concentration of C, that's C.
Why specifically is he saying C? It's the concentration of C. That's the, I think you said it. It's the colored one, right? The spectrophotometer can't measure B. What really the spectrophotometer is measuring is C, isn't it? So it's able to see the green solution. And then you take B, your cuvette, and then you have your concentration there and your absorbance already. You know what you started with. So that's what we're going to do. So you can use a data point from any graph where C is known, which we know C at the start for all three of them, right? So use your starting C because that data was specific to you. And then look at the absorption and blah, 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 and you calculate at any point that you so choose. All right, so once we find little a, now we're able to go ahead and calculate what all of those concentrations will be. So did you get 5.0? And then just recognize the reason why they're coming up with the units. You wouldn't be really asked to calculate little a. Maybe they would. But it's just recognizing that your units here for absorption and then molarity and centimeters are in the denominator. So that would be why it's in the denominator. Absorption, just you use like a capital A, but there's really not a unit there. All right, so now that we know A, we can go back and we can calculate the initial rate for each experiment. So experiment 1, so how are we going to find our initial rate? You're going to do change in concentration over change in time. That's what rate will be equal to. And then this is negative because we have the rate of disappearance, so we're going to put a little negative sign in front of there. So we're going to do a final minus an initial for here and then time also. So you can pick the spots that you would like, but the easiest spots to pick certainly are the ones that are already given to you. So here we're going to find concentration. And we're picking, I believe, from experiment 1, your initial absorption is 0.5 there, which means that the concentration of C is, you're calculating concentration for that one. So absorption is, I'm just looking at what they gave you. For experiment 1, yeah, you have to pick a final minus initial spot and then subtract them. So I'm just going to quickly go back here so that you can see with me what they're looking at. All right, so for experiment 1, we're going to find our change in concentration over change in time. This is our initial starting point, right? So we don't need to calculate the final spot. We already have our initial, because our initial concentration for the green species was 0.10. So we need to find some spot later on here. So I think that they're using 60 seconds here. So this is why they're choosing this point, and then they're just kind of going like this. So roughly, that's why the data is there, is 0.375. They're just calling this sort of like a halfway point. That's why it's really tricky, but you could have called it like 0.4 or whatever you're going to call it. Our data might just be slightly off. So this would be why we have to calculate the concentration at this point, because we don't have it. So we would do A equals ABC here, and then we're solving for C. So C is equal to absorption over AB. And the absorption is roughly 0.375 over our little a we already solved for, and then times the path length. And then that's your final spot. So then you can do change in concentration over change in time. So we can head back to that data for you. All right, so that was 0.375, and then our little a is 5 times 1. So the concentration final was 0.075 minus what they gave you, which is 0.10 to start with, and then that was 60 seconds later. Now, had you chose the 120 seconds, you may have chose that and perhaps you plotted that to be about 0.25. You could have done that. That might have been easier for you to see, so maybe you just chose to use that point instead. Just choose the points that are easiest to see. So change in concentration over change in time, our initial rate for experiment 1 is 4.2 times 10 to the negative fourth. And then rate is always molarity over seconds. All right, so now we're going to look at experiment 2. So go back to your data. We already have the concentration of C for the initial, so we're really just calculating the final. So I'll go back there with you. I think it's probably easiest to pick a point that you can easily read. I probably wouldn't have picked that halfway point. But this one looks really easy to read anyway, so this is probably 0.750. I just want to show you here, you probably could have used 0.250 and just make sure you chose 120 seconds. That might have been easier to read, but you should still get the same data. And then like even here, this is easy to see also. All right, so then you're going to choose, again, A equals A, B, C. So C is going to be equal to 0.750 over 5 times 1. And then you're going to solve for change in concentration over time for that one. Same thing here. C equals 0.250 over 5 times 1. And then you get your concentration there. And then subtract from what the initial concentrations were. Just super time consuming. So I'm going to let you guys solve all that. I'll leave this data up so you can check your answers. Okay, so once you have that data, now look at the table that I made on the board, or the one that's up here. You are making the exact same table that you saw like however many slides ago, right? Except you generated it now, and now you determine the data. So find the rate law for this is the same way that you would do it as always. You can calculate it or you can just look. So if we're finding B, we want to find where B changes but C stays the same. So C stays the same in experiments 1 and 3, but changes in 1 and 3 here. So this is a times 2, and this is a what? Times what? You can't see that? Almost a times 2. Why is it not exactly 2? Because this is lab data, and if you guys actually did this in lab, I guarantee you it would be like 1.7 or something, and then you'd be really struggling. It's because you do this in the lab. Your numbers don't come out to perfect 2s and 4s. You kind of have to like estimate and see where it is. So this is double, so what's that order? First order, right? So this is with respect to B. B is going to be first order, but we don't need to write the 1, so we're just going to erase that. And then C changes here, so this is a times 2, and this is a roughly times 2, so now it's C. So our rate is equal to K, and that's it. All right, realize that your work on this is imperative. If you just, this again is just showing you all the math. Do you see that? So it's helpful to know how to do it with the math, but it's not necessary. You could usually just look at it and eyeball that to come up with first orders. So the rate law is this. If you just wrote this as your rate law, you would never get credit without doing all the work, right? Because they need to see that you saw that the rate. So if they say justify your order, you can show the math like I showed you all those times before, or you could just show, like you could write in a sentence like the concentration of A doubled and the rate doubled, therefore it's first order, something like that. But you have to be able to justify it somehow. All right, so find the rate constant for K. So you guys did this already, so you're just going to pick any experiment and plug in the data for that specific. You solved already, you made this table yourself essentially. So pick any experiment, plug in your data. All right, so you plugged in any data. You should have all gotten at least exactly this or close to this. And then remember that the units are essentially m times m, so that's m squared. So you would need an m and an s in the denominator to give you an overall m over s. And then the overall order is second. Make sense? The end. So